Hello, welcome to the hobby world of Dr. Mike. In this video we'll be talking about the output driver I'm using for my pinball conversion project. The output drivers for the most part need to switch coils associated with relays and solenoids. Even though I'm replacing the main logic board in the pinball machine, there are still a lot of coils associated with relays and solenoids on the playfield and in the head of the pinball machine. You have to be careful on what device you select for switching these coils. I'm using a triac. A triac has a very unique characteristic which allows the current to continue to flow even though the gate is turned off until the current reaches a 0 point. And the current will reach a 0 point in an AC system. The triac provides a nice smooth transition for current turning on and turning off, which limits the voltage spikes across the coils. We'll look at what happens when a contact is used to switch a coil. When a contact is used to switch a coil, there are a lot of voltage spikes. These voltage spikes can corrupt my logic board. I need to be careful to protect my circuit from that noise. I don't want my pinball machine to be acting like a poltergeist has taken control of the pinball machine.
Here's the circuit I'll be using as my output driver. Basically, I've got an opto-isolator triac driver which provides about 7,500 volts of isolation between the AC and the DC systems. It's an LED just to let me know when it's being driven, and a 100 ohm resistor to limit the current to less than 20 milliamps. The microprocessor can source and sink about 60 milliamps, so we're okay here. The opto-isolator triac driver then drives a triac. 270 ohm resistor and the 0.22 microfarad capacitor are there to filter out any noise from the triac gate. Turns out the triacs I'm using are fairly sensitive. Here's the schematic I'm using to look at the voltage across the coil and the current through the coil. Got the 24 volt AC supply that drives the coil. Got the triac. Basically I have the clamp on ammeter here, 10 turns, so I can change the effective ratio from 50 amps to 0.5 volts to 5 amps to 0.5 volts for better resolution. Then I'm tapping the voltage off the coil and then looking at the current. This is where the triac turns on and starts conducting current. The current waveform looks a little bit fuzzy due to scaling and resolution issues. You see this little blip here, that's where the current is actually transitioning from negative to positive, and you'll see another blip on the voltage waveform when it transitions from positive to negative. I know with my program that the gate will turn off after about 50 milliseconds. The triac has already started conducting for this negative cycle. The current will continue to conduct until it hits 0. Then it'll stop. There's a little voltage spike here, but that's not too bad. Here's another waveform. Again, the triac starts conducting at this point, different point on the waveform. 50 milliseconds later, it turns off. And again, the current continues to conduct until the waveform reaches its natural 0 point and then turns off. And again, another waveform. Here the triac turns on at a point closer to the voltage zero crossing. I get quite a bit of current DC offset, but that dampens out pretty quick. Again, 50 milliseconds after the triac is turned on, we turn the gate off, and the current continues to conduct until the 0 point. I had to use a different circuit to compare the voltage and currents of a relay switched from a triac and a relay switched by a contact. The current probes I had were far too sensitive to the noise being generated. So this circuit I used a 1 ohm resistor, so the voltage going into the oscilloscope, 1 volt represents 1 amp. Then of course to actually measure the true voltage across a coil, I need to subtract the voltage across a resistor A2 and B2 from the voltage across the combination coil and resistor A1 and B1. There's a lot of arcing in these contacts, which generates a lot of electrical noise in the pinball machine. Here's some plots of the waveforms on the latest test. You can see the waveform switched by the triac at the beginning. It's nice and smooth. There's a little bit of noise that's picked up from the circuit that's switched by the contact. At the end here, it's nice and clean and smooth. The relay coil switched by the contact, on the other hand, is very noisy. Current isn't quite established here. It tries to establish, and then while the contact is closing, it swipes, and you get small periods of time where it makes and breaks contact. And then at the end, when it opens up, what happens, you'll have a small amount of arcing where the current will conduct through the arc for some period of time, and then it's chopped off. Here's chopped off at about 0.2 amps. Then there's a very large voltage spike. There's another set of curves. Again, that switch by the triac is nice and clean and smooth all the way through. This time, the current is established, and while the contact swipes while it's closing, there's small periods of time where it breaks and you get an arc. That's what we're seeing here. But the current continues. And the voltage spikes aren't that bad, but there are some spikes here. In this case, the current chopped at about 0.25 amps. And again, you can't see it, but the voltage is clipped at about minus 80 volts. Given the slope of this decay, I calculate that the voltage was actually about minus 150 volts, which is pretty good for a 24 volt circuit.